Hi, we have been discussing the eigenvalue problems. The first thing we discussed was the free particle problem, and then we went on to the infinite square well potential. Okay, so we saw the eigenvalues and the eigenfunctions for the one-dimensional case, and it's easy to generalize it to 2 and 3 dimensions. Okay, that's what we'll see today. And then when we go to 2 and 3 dimensions, there is also the issue of degeneracy. And then we'll discuss a small part in the finite well potential. So the questions asked from finite well potential. So by looking at the previous question paper, we see that the questions asked from the finite well potential always comes from one particular part, right? It's about counting the number of bound states. Okay? So that's the only thing that we'll discuss from finite square well potential. So here is infinitely deep potential well in 2 and 3 dimensions. First we go into 2-dimensional case. Okay. In the 2-dimensional case, all right, we just the wave function, all right, the energy eigenfunction is simply obtained by taking the 1-dimensional cases, okay, the 1-dimensional one for the x dimension, nx by x by a, right, corresponding to x direction. This is one number, and then one for the y dimension, okay, square root of 2 by b sine ny by x by b. Okay, so here this a and b are the widths in the x and y directions respectively. Right. Now, if it's a square potential well of infinite depth, in that case a is equal to b, and then we get this thing. Right, it's 2 by a sine nx by x by a sine ny by y by a. Alright, and the energy eigenfunction. Alright, so if you want to obtain the eigenfunction, you just multiply the corresponding eigenfunctions. In this case, alright, you take the x the eigenfunction corresponding to the 1 dimension x dimension, take the eigenfunction corresponding to y dimension, then multiply them, you get the eigenfunction corresponding to the 2-dimensional case. For the eigenvalues, they get added. Okay, so the eigenfunctions get multiplied and the eigenvalues get added. Right, it's understandable because the total energy, right, you have got one more contribution to the energy, so you just add it up. Okay, so that's the energy eigenvalue. So remember, we are using two different numbers here, nx and ny. All right, we can change them independently. And in 3 dimensions, again, you just introduce one more factor, that's all. Okay, nothing particularly complicated about it. And then again, in the energy eigenvalue, you just add the contribution from one more dimension. Okay. For a cubic box, which means that a is equal to b equal to c, in that case, you get this answer. Okay, just put a equal to b equal to c, and this is the energy eigenvalue. Okay, that's easy. Now, the ground state corresponds to nx equal to ny equal to nz equal to 1, because I said that the lowest value possible that can be taken by this nx, ny and nz is 1. Okay, that's the lowest value possible. Okay, if you take 0, if you take nx, ny or nz 0, you see that there is no wave function. All right, the wave function disappears. Okay, so we don't have that. All right. Now we go into the issue of degeneracy, right? So if let's say that the energy has a given value, right? Let's say that the energy has a given value. Let's talk about the 3-dimensional potential well. The energy has a given value. Okay, that means that these are constants here. These are constants. If you say that the energy has a given value, that means that this value is fixed. Right? We have fixed this value. Okay. But then you will see that there are different ways in which you can get that fixed value, because you can change, all right, for different choices of nx, ny and nz. Okay, you can get the same value for different choices of nx, ny and nz, and then we say that there are different states corresponding to the same eigenvalue. That's what's called degeneracy. Okay, so different eigenfunctions corresponding to the same eigenvalue are called degenerate. Okay, so if corresponding to the same energy, you have got two possible states of the system, we say that it's twofold degenerate. Okay, it's degenerate. That eigenvalue, that energy eigenvalue is degenerate. All right, there can be 3-fold or 6-fold degeneracies. Okay, so you can have any number of eigenfunctions depending on the situations. The degree of degeneracy can change. Okay, the number of distinct eigenstates corresponding to the same eigenvalue is known as degree of degeneracy. Okay, that's the degree of degeneracy. Right, so you take a particular eigenvalue, count the different states with the same eigenvalue, and that number is called the degree of degeneracy. Okay, all right. I hope that's clear. The same energy value, right? Because you have got nx, ny and nz. The same energy value can be obtained for different combinations of nx, ny and nz. And then we say that there's a degeneracy, right? Because if you change nx, ny or nz, right? If you interchange, for example, let's say nx equal to 1, okay, nx equal to 1, ny is equal to 2 and nz is equal to 4 or something, all right, 4. Okay, this gives you a particular value for energy. This gives you a particular value for energy, and then you can get the same energy, all right, for a cubic box, for example. For a cubic box, let's talk about a cubic box, all right, A equal to B equal to C. Okay, we said 1, 2, 4. Even if you take nx equal to 2 and ny equal to 1, you will get exactly the same energy. Am I right? You will get exactly the same energy. All right, but the wave function changes. But the wave function will change. All right, if you change nx and ny, you have a different wave function, or you have a different eigenfunction. That means that you have a different physical state corresponding to the same eigenvalue. All right, that's why we say that there is a degeneracy. Now, such problems have been asked from infinitely deep square well potential. Let's look at a problem. All right, a particle of mass m is in a cubic box of side A. It's in a cubic box of side A. The state of the particle is an eigenstate of energy. All right, the energy is given. Right, 14 pi square h cross square divided by 2 ma square. Find a possible eigenfunction. Right, find one possible eigenfunction. Find also the degree of degeneracy. Find also a degree of degeneracy. All right. So comparing it with this thing, we had En for a cubic box. We had En is nx square. En equal to nx square plus ny square plus nz square. Okay, for a cubic box we had multiplied by pi square h cross square divided by 2 ma square. Am I right? Yes. So you look, we need nx square plus ny square plus nz square to be equal to 14. Right? We need nx square plus ny square plus nz square equal to 14. Okay. So if you look at this, one possible choice is to take nx equal to 1, ny equal to 2, nz equal to 3. Okay. Now, if you square them and add, okay, 1 square plus 2 square plus 3 square, that's equal to 1 plus 4 plus 9, okay, that's 14. Okay. So that's one possible combination, nx equal to 1, ny equal to 2, nz equal to 3. Right? Now, again, you can just change nx and ny, and you'll get exactly the same eigenvalue. You'll get exactly the same energy. You could take nx equal to 2, nx equal to 1. All right, and then you will get the same eigenvalue. In that way, you can look at permutations of 2, 1 and 3 to obtain the same. All different combinations of 2, 1 and 3 will give you exactly the same energy. All right, but corresponding to each permutation, the wave function is different. Okay? So, for example, we can just write it like this. All right, the combinations 1, 2, 3, nx, ny, nz is 1, 2, 3. It can be 1, 2, 3. Could be 1, 3, 2, which means nx1, ny2, nz2. Sorry, ny3 and nz2. All right. You could also have 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. So we have got 3 different numbers. You have got 3 factorial combinations, 3 factorial ways in which you can combine them. That's 6. All right. So the degree of degeneracy here is 6. The degree of degeneracy here is 6. All right. Now, for example, yeah. So in this case, the degree of degeneracy is 6. You have to count the number of combinations. Okay. Okay. Now, if any two numbers are the same, for example, you are looking at a combination for 1, 1 and 2. All right. Not this case, some other case where nx is 1, ny is 1 and nz is equal to 2. Then the interchange of them does not give a different wave function. All right. So you shouldn't count them. That's how you count the degenerate wave functions. All right. So if you have a combination 1, 1, 2, the interchange should not be considered as a different wave function. Okay. Then we need to take only combinations like 1, 1, 2, 1, 2, 1. Okay, 1, 1, 2, 1, 2, 1, 2, 1, 1. All right. Is there any other combination allowable? No. In that case, we see that the degree of degeneracy is just 3. Okay, that's just an example. For example, in this case, it is 1 square plus 1 square plus 2 square. So the energy is 1 plus 1 plus 4. Okay, that's 6. The energy, the n square value. Okay, instead of here, if you have a 6 here, That means the combinations are 1, 1, 2, 1, 2, 1, 2, 1, 1. Is there any other possible value of obtaining 6 from nx, ny and nz? You have to check, and in this case it seems that there are only 3 possible values. Alright. Okay. But if this was different, then it goes up, alright, it goes up to 6. Right. Okay. So that's how you find the degree of degeneracy for infinitely deep potential well. Such questions have been asked. This particular question was asked in one of the previous NET JRF examinations. Okay, so that's how you do it. Let's look at a few more problems from the infinitely deep potential well. If En denotes the discrete bound states energies of a particle in an infinitely deep one-dimensional potential. Okay, this is a problem from one-dimensional well. This also was taken from a previous question. Then En plus 1 minus En. What is En plus 1 minus En? Okay, so it's easy to find if you remember the eigenvalue En. What's En? So En is n square pi square h cross square divided by 2ma square. Okay, so let's just write it down. That is, for En plus 1 is then n plus 1 square pi square h cross square divided by 2ma square. Okay, so that is and minus En is n square pi square h cross square divided by 2ma square. Alright, so En plus 1 minus En simply is n plus 1 square minus n square and then pi square h cross square divided by 2ma square. Alright, what's that? It's n plus 1 square minus n square. So it's n square plus 2n plus 1 minus n square. So it's 2n plus 1 minus n square. Am I right? Okay, let's check. So let's just do this is n square plus 1 plus 2n minus n square. So it's 2n plus 1 multiplied by pi square h cross square divided by 2ma square. Okay. Now what is this? This is the energy eigenvalue corresponding to n equal to 1. So you can write it as 2n plus 1 multiplied by E1. 2n plus 1 multiplied by E1. That's the answer that we have here. Okay. I hope this is clear. Right. This is not very difficult. You know the expression for En, so you just do them and subtract them. All right, that will give you 2n plus 1 E1. Here's another problem, again in one-dimensional potential well. An electron in a one-dimensional infinite potential well defined by V of x equal to 0 for minus a less than or equal to x less than or equal to a. Okay, so you note that the width here is, let's write the width is 2a. All right, don't forget that the width here is 2a. Okay, v of x is equal to infinity otherwise. Goes from, also you see that it's a symmetric potential. It's symmetric potential. All right, it's symmetric. Goes from n equal to 4 to n equal to 2 level. So there's a transition from the energy level n equal to 4 towards n equal to 2. Alright, so a photon will be emitted corresponding to that particular energy difference. That's what we know about these things. The frequency of the emitted photon is given. The frequency of the emitted photon is given. Okay, find the width of the box. Find the width of the box. So we know that for a symmetric well also, we are talking only about the energy eigenvalue here. So that's fine. That's fine. We are talking only about the energy eigenvalue. So it's the same. Alright, what's the energy eigenvalue? We can write it as En is equal to n square pi square h cross square divided by 2ma square. Right? In this case, a is equal to let's write as 2ml square. Well, L is the width of the box. Right? In this case, L is equal to 2a. Have to remember this. L is equal to 2a. So this is, remember that whatever appears here has to be the width of the box. So this becomes n square pi square h cross square divided by 2m and 4a square. So that would be 8ma square. Alright, En would be n square pi square h cross square divided by 8ma square. Alright, now what we just do is that we see that the transition is from n equal to 4 to n equal to 2. So you say that E4 minus E2, that energy difference between these levels, okay, it goes out as a photon of n of frequency given, frequency is given, okay, 3.43 into 10 raised to 14 hertz. Okay. So the corresponding energy is h nu. The corresponding energy is h nu. Okay. So this is the equation that we will use. E4 minus E2 is equal to h nu. Alright. So you take E4 from here, take E2 from here, subtract them, equate it to h nu. Now we can solve this to find A. Right. You will see that the only one unknown in this equation will be A, and you can solve for A. Okay. So you can complete the problem. I hope you understand how we do this thing. Okay. The only thing you have to be careful is when you see the problem, you have to see what's the width of the box. All right. Don't just write n square pi square h cross square by 2ma square. You have to see the width of the box. In this case, the width is 2a. All right. So that's the only place where you can go wrong here. So you just solve it. Finally, you see that a square is 3h divided by 8m nu. It's the, okay, let's write v as the frequency. All right, that's v we'll write as the frequency, and then you see that twice a, that's the width of the box, is 17.84 into 10 raised to minus 10 meter. It's of the order of 10 raised to minus 10 meter. Okay. 10 raised to minus 9 actually, it's 1.7 into 10 raised to minus 9. So it's in the nanometer range, the width of the box. Okay. Alright, now we go to finite square well potential. Alright, so the solution of this, finding the solution of this is a bit more involved when compared to infinite square well potential. Alright, but we'll do only one kind of problems from here, where we find the number of bound states. Alright, we find the number of bound states. Alright, so here we have got potential V for x less than minus a, okay, and sorry, it has to be v both places. All right, so the potential is v between minus a and plus a. All right, minus a and plus a. All right, and no, it's 0 for minus a between minus a and plus m. Sorry, it's 0 between minus a and plus a, and it's v elsewhere. All right, the potential outside is v. Potential outside is v, and it's 0 inside. Okay, sorry, it's 0 inside. That's what we have here. It's 0 between minus a, and outside it's there's a potential. All right, a finite height v. In the earlier case, what we saw was that it was of infinite height. Right? These walls were of infinite height. In this case, it's not infinite, it's finite. Right? Now, remember, just so that we don't confuse, let's denote the width of the box as L. Let's denote the width of the box as L. All right? In this case, we see that L is equal to 2a. All right? Just so that we don't confuse about this, we'll denote the width of the box with the letter L, and in this case, L is equal to 2a. All right? Now we'll look into how we count the number of bound states. All right, the solutions, you can look at the solutions, you have to solve them graphically, etc. But if you look at the solutions, you will see that there is one symmetric solution if v is between 0 and pi square h cross square divided by 2 ml square. Okay, so you see that however weak the potential is, however weak v is, if it is above 0, you will always have at least one bound state. Okay, this is what it means. So the solution will tell us that if v is between 0 and pi square h cross square divided by 2 ml square, all right, then we see that there's at least one bound state. All right, no matter how small v0 is, there's always at least one bound state. Okay, this is something that we have to remember. All right. This may be a bit surprising, all right, even if energy is much higher than the potential energy of some particle, there's always at least one possible bound state. All right. Now this part, it's easy to remember because you see that this is actually E1 of infinite. I'm just giving you a way to remember this. This is actually E1 of infinite square well of width L. Am I right? This is actually E1 of infinite square well with width L. This means that if the energy is less than the E1 in the case of, if the potential is less than the E1 of infinite square well with width L, then there is at least one bound state. All right. Similarly, the analysis will show that if V is between E1 and E2, okay, if the potential energy is between E1 and E2 of the infinite square well. All right, this is not this well, but of the infinite square well, and just writing this so that we remember this easily. All right, if it's between E1 and E2 of the infinite square well, then we say that there is one symmetric and one antisymmetric. All right, at least that means there are two bound states. There are two bound states. Okay. Now again, you continue this and you see that there are three. If it is 4 pi square h cross square, if V is between 4 pi square h cross square and 9 pi square h cross square divided by 2ml square. Okay. So we see that we can obtain a general formula here. The number of bound states, all right, the number of bound states is n. Okay, if number of bound states is, okay. So we say that if the potential energy is between n minus 1 square pi square h cross square divided by 2ml square and n square pi square h cross square divided by 2ml square, then there are n bound states. Okay, then there are n bound states. N here is the number of bound states. Okay, here you see that n is actually 3. Okay, because it's n square, we are written it as n square. So here n equal to 3. So as we said, there are 3 bound states here. Okay, here n is 3. This is n minus 1. N minus 1 square is 4. All right. So if it is between n minus 1 square and the rest is actually the E1 of the infinite square well, so it's easy to remember. Right, this is easy to remember. This condition is easy to remember. So if a potential is given and you are asked to find the number of bound states, number of possible bound states, what you do is that you write it in this form and then you can know how many bound states there are. And this condition is easy to remember because the part appearing here, all right, the part appearing here is actually the infinite square well potential energy eigenvalue. All right, this is actually E1 of infinite square well potential. All right, so it's easy to remember. All right, let's do a problem, then it becomes clearer. Right, find the number of bound states for the finite square well potential. Okay, here it's given, it's V for x less than minus a by 2 and V0 for x greater than a by 2. All right, so that's that's the specification of the finite well, but we are interested in the width. What's the width here? The width is actually it's between a by 2 and minus a by 2. Okay, so the width is actually a. The width here is actually a, not 2a. Okay, some case you have to be careful about the width. Okay, when r, find the number of bound states for the finite square well potential when r is equal to 1 and r equal to 2. And what's r here? They have given in the question itself. R is equal to square root of m a square v0 divided by 2h cross square. Okay, h bar square. Right. So we take the first case. We take the first case and they have given r equal to 1, which means that square root of m a square v divided by 2h cross square is equal to 1. Okay. From here we can solve for v and we see that v is equal to 2h cross square divided by m a square. Okay. V is equal to 2h cross square divided by m a square. Right. Now we have to compare it with the form that we are familiar with. Okay. So here the width of the box is L, so we will write it in terms of L. All right. L equal to A. So V is equal to 2h cross square divided by ml square. Okay. I am just using L as the width because sometimes it can be A or 2A and then we don't want to get confused. Right. So we will take this L as the width of the box. Okay. So we see that V is 2h cross square divided by ml square. Right. Now we can compare it with the nearest thing that we are familiar with. We will compare it with pi square h cross square divided by 2ml square. Okay, pi square h cross square divided by 2ml square. All right, we'll compare it with the nearest thing corresponding to the E1 of infinite square well potential. All right, that's the way we wanted to remember it. Okay. You see that there's a pi square by 2 here. Okay, there's a pi square by 2 and there's a 2 here. So they differ only by this factor. So we see that pi square by 2 is actually greater than 2. Right, pi square by 2 is actually greater than 2, isn't it? Because pi square is 3.14 square. So divided by 2 is greater than 2. So we see that this thing, the potential energy, is actually less than pi square h cross square divided by 2ml square. Okay, so here n is equal to 1, so the number of bound states is 1. That's it, right? So in other words, the potential energy is between 0 and pi square h cross square divided by 2 ml square. So the n here is actually 1. So the number of bound state is 1, right? Similarly, we can do the case for this equal to 2, and you will get V is equal to 4 h cross square divided by ml square, right? 4 h cross square divided by ml square. So we can easily compare this with 4 pi square h cross square divided by 2 ml square. Right, we can compare it with 4 pi square h cross square divided by 2 ml square. So if you look at the difference again is of pi square by 2. So this is clearly less than 4 pi square h cross square divided by 2 ml square, and it's greater than pi square h cross square divided by 2 ml square. So there are two bound states in this case. All right. So you compare this with the formula. If n minus 1 pi square h cross square divided by 2 ml square is less than V, which is less than n square pi square h cross square divided by 2 ml square, then we have got n bound states. Okay, then we have got n bound states. Okay, so it's not very difficult. Only thing is that you change it into the, compare it with the nearest standard form of n square pi square h cross square divided by 2 ml square. All right. Okay, such problems have been asked, and by looking at the previous question papers, all right, we see that this is the only kind of question mainly that's been asked from finite square potential. All right, so we don't want to spend more time on this. We'll move on to more important sections. So this is the only thing that we'll study in this part. Okay. All right, there's another problem here. There are only 3 bound states for a particle of mass m in a one-dimensional potential well of the form V of x equal to 0 between minus a by 2 and a by 2. So here again the width is L is equal to a. All right, let's remember that the width L is equal to a. The depth of the potential well satisfies the condition. All right, what's the condition satisfied by the depth of the potential well? So that's easy. It's given that there are only 3 bound states. There are only 3 bound states. All right. So if there are 3 bound states, that means you would have the upper limit as 3 square pi square h cross square divided by 2 ma square. Okay. This has to be greater than V. This has to be less than 2 square pi square h cross square divided by 2 ma square, because our condition was n minus 1 square pi square h cross square divided by 2m less than V less than n square pi square h cross square divided by 2m. Okay, this is what we saw. If this is the condition, then there are n bound states. All right. So they have given that there are 3 bound states, and they have asked the condition. All right. They have asked the potential energies between what? Okay. Depth of the potential well. All right. So we write it like this. So if there are 3 bound states, then 2 square pi square h cross square by 2 ma square will be less than V, will be less than 3 square pi square h cross square divided by 2 ma square. That's the condition. We wrote it directly. All right. Now you look at the solutions. Does it appear somewhere? 2 pi square h cross square divided by ma square less than V0, 9 pi square h cross square divided by 2 ma square. I think this is correct, because this 2 we can write as 2 square divided by 2, and then we have the condition here. You see, 2 square pi square h cross square divided by 2 ma square less than V less than 3 square pi square h cross square divided by 2 ma square. All right. So this 2 pi square h cross square by ma square, we can write it as 2 square divided by 2 pi square h cross square divided by ma square. So option A is the correct answer.